start recording. On the one that you give answers to? I don't think he sent it to me. Okay. This problem? No. Oh yeah, I didn't know how to do that either. This one, this is the CB and K block, which is not on this one. So. This one, okay, that page is missing from the one he sent me, but I can draw it and do it on this. Okay, so this has to do with friction. The car is traveling sinusoid straight velocity, which is accelerating this way. I should make this down. So this is saying that friction is acting on the car, which would act in the opposite of the direction of motion, which is the friction force. Frictional force is what I'm thinking. So I think this is how I would do this problem. How did you start?
How did I start?
How did you start?
How you just start?
I haven't tried it. How would you start? You don't have to fill in that part. Just
I would start with the equation like v squared over r to get the acceleration.
yeah. I drew this in the wrong direction. So if it went too fast, flip this way. Oh.
Does this mean they're just like before the this one? Since they didn't give me
It says derive the formula, so you don't have to find the number.
I think the maximum loss in
Coefficient extent.
so
Basically, if this car goes too fast, it's gonna slip this car. It's just gonna go like a tangent circle instead of into a straight line. And it's the friction between the tire that keeps that from happening. So I would say equals FA which is equal to the frictional force. So yeah, M squared over R is equal to the normal force times the static coefficient of friction. And then equals mg. L is going to be the square root of R G. Because static friction is what's keeping it, is what's causing the circular acceleration.
okay. This is okay. Here's two.
Well, welcome to Studio. I come in over time. Are there any other questions you'd like to any topics?
I have one from PHYS123. Part B, I don't understand tension in the middle.
Yeah, let me draw blocks are connected by has mass.
Probably not.
So what is the tension at the midpoint of the rope? It's asking for what's the tension here, which is half, because you have the weight of the rope. Half of the weight of the rope is above and half of the weight of the rope is below that point. So you would use that when you analyze the tension. How do you think you would start with this one? So the acceleration is 0? Yeah. What would you do first?
the forces on the top equals the forces on the right.
Yeah. Like say draw a three-body diagram at that point. Say what forces are acting right at that point. So what forces are acting?
200 newton on the top. 100 newtons on the top.
Right here. Like right here. This force is being applied there. So oh wait, there's a deceleration.
Oh yeah.
Did you? Okay, so there is an acceleration. So acceleration is equal to what's that number?
3.52.
Okay. This, but as far as what I said about this point, is still this force is applied up here, not right here. So we don't need to take it into account. We just need to take into account the acceleration that it comes.
So the gravitational force applied on the that's 7 kg. 2 plus
Yeah, so there'd be 7 kilograms times g down upward tension. This is what you're trying to solve for, right?
and tension plus the force down here to MA.
Yeah.
Oh, okay.
Plus MA plus tension minus 7g. You know A. Tension is going to be mass times acceleration. So the mass is mass of the system. Or just I would just use the 7 kilograms. I think would be correct amount to use, because you can also take this whole log, right? Take this tension up, 7g down, and then acceleration. Yeah, so I would use tension equals 7 times acceleration plus g.
So F equals the sum of force equals tension minus 7g.
Yeah.
Does that make sense to you? Yeah, that's the right.
Yeah.
Good.
Okay. Any other quizzes or anything you want to go over? Homework questions? Didn't understand.
Oh, the part B.
Which test is this?
You don't define.
Yeah.
This question number 29.
Yeah. Which number is it?
Oh, that one, the first one.
The first one?
Yeah,
Oh,
this
okay. So. All right.
you're concerned about question in part B. So loop goes around vertical, constant speed. A car has to pass. There's a speed. We're doing as a radius of r. What is the magnitude of force in the car at the bottom of the circle? And then B is how heavy would a 20-pound person feel when at the bottom of the circle? Okay. So, do you understand what it means by the force that you feel? No? Okay. So, when you're how heavy would you feel? So, when you feel a force, it's usually due to contact with the surface, right? So you can feel your weight is pushing down on the ground, and that same weight is pushing up on you. Mm-hmm. So, but you don't feel your own weight, you feel the ground's response to your weight, so you're feeling normal force, right? So the force you feel is the normal force. Right? So it's asking, what is the normal force for a 200-pound person at the bottom? In the car. Yeah. Okay. So you could say the person's going at that velocity, at that radius, only their mass is 200 instead of 350. Okay. But this is in pounds, so you're also gonna need to convert it from pounds to kilograms. Yeah.
Did you give us conversions?
He should. I don't.
2.2.
2.2. No, that's 2.2. So you would have 2 kilogram. It's gonna be the weight. It's gonna be mg. Like, pounds are. Does this convert to kilograms or does it convert to newtons? Kilograms. Converts to kilograms. Yeah. So what did you get for this?
90.9.
Which is a reasonable weight. So when you have a person down here, normal force is up and she's down. You have the acceleration is upward towards the middle of the circle. You know how to do this part, right? F C equals M squared R, which is going to equal the normal force minus mg. So the normal force is going to be mg squared over r plus mg. Anything? Are there any other questions on the test you'd like to go over?
Number 6.
Number 6. This is the same test. Oh, I'm gonna turn this one down. So this is part A, part B, both parts. Okay. Oh, this was a whiteboard. Whiteboard problem. Yeah. You have an automated child launching device, as shown below. The length of the swing's rope is 4 meters. The child has a mass of 44 kilograms. What spring constantly require so that it can only compress 40 centimeters? If it can only compress 40 centimeters so that you will launch your child to a maximum of 45 degrees. Degree angle. What was the max speed your child will experience? Alright. So for the first part, you have these angles are 45. Yeah, it's here. I would use energy methods, like the professor has done here very faintly. So energy before, same as energy after. When the child's down here, they have only spring energy, which is 1/2 kx squared. And then after, they have all potential energy because this is the highest point they go to, velocity is 0 when they get to their highest point. So that's 1/2 mv squared. That's the wrong thing. I meant to write mga, where high h is this distance. So here we're solving for k. So k is going to equal 2mgh over x squared. We're given x as 40 centimeters. We're given x as 44 kilograms, but we need to calculate h because the distance we're given is the 4 meters here. We can do that using trig. Would you like to try calculating h?
Four minus 4 square root 2.
Okay. Wait. 4 minus
4 over square root 2.
Is this the same as 4 sine 45? Yeah.
Yeah, that's right.
It's 2.83.
What is it equal?
2.83.
2.83.
So H is 1.17.
Oh, okay. 1 point. This part is equal to 2. So it's equal to 1.17. Okay. So we have H, we have X, we have mass. You should be able to plug in and then solve for K. Um, 244, 1.17 over 0.4 squared.
It was hard to come up with equation, like half times k times x squared equals mgh.
Yeah, that's the hard part.
Yeah.
So how would you have started figuring out that part of the problem? Like, if we had a different problem, okay,
Yeah, this
down here, you have a, well, it's compressed, natural length is up here, this is x, and then you want it to go a distance h up in the air, is how high you want it to go. And you need to solve for the spring constant, say, or you're given the spring constant, you need to solve for h. Where would you start this problem?
potential energy equals to
Okay, so the initial potential energy. What will the initial energy equal to? Yeah, it's equal to the final energy. But I'm saying, like, from this equation to this next equation, what energy does it have initially? Yeah, it has spring energy. Right, so it has energy of the spring that's going to be equal to its final energy, which is gravitational potential. So you have these equations that should be on the formula sheet. Yeah, u spring kx squared over 2. Gravity is this in general. Yeah, mg.
sometimes there's like half k times x squared equals half minus times y squared.
Yeah, that's when you have velocity. So if I said, what is, you know x, you know k, you know h, or you don't know h, but you just know k and x. But you know that, like, say right here, how high is, how fast is the ball going to be going? Then, in this case, what kind of energies do you have initially?
one of the balls right here. Yeah, you just have to spring. But what do you have here? Kinetic energy.
Do we know H?
So for spring energy, one pairs from the formula sheet. The formula sheet will give you this one GH, and we'll give you this one, LV squared. That's why it just has to do with, those are really the three energies you'll have to use, although sometimes you'll have energy initial equals energy final plus the work by non-conservative forces, which are, they are frictions basically.
Okay.
So the non-conservative forces are going to be friction in those problems. And then you just do all the same stuff and you say what work did friction do on the final energy side, because it's going to have less energy at the end than it did when it started, because some of that becomes heat and whatnot through friction. Does he have that formula on you? I don't know what's on the equation. Oh, change in energy equals. It's just equal. Yeah, that's another way to put it.
So in this equation, G is negative.
No, G is positive. G is always positive. You simply write negative G. Yeah. It's in all these equations, anyways. It writes G as positive, so it's better.
G is positive. This one is the change in energy.
So this is basically what I wrote up here. If you did change of energy, it's going to be energy initial minus energy final, which is going to, so if you subtracted this and brought it over to that side, it'd be equal to the work. Yeah, this is just the way I'm going to write it, whereas this is the way the professor writes it. Yeah. So they mean the same thing. Part B. Where'd that problem go? This problem?
Yes.
Okay. Okay. So, what maximum speed will a child experience? When it says maximum, what does that make you think as far as where it's going to experience the maximum speed?
and it goes from like here to here. Since gravity is going to be slowing it down, the maximum speed is going to be at the bottom. Yeah. So,
You're using that 45 degree angle. Yes, but you don't have to actually incorporate that at all to your analysis because its maximum speed is always going to be right here, right? Even if it went up to 60 degrees and came back, the maximum speed would still be the same. You've already solved for your spring constant, whatever that ends up being. So you could use, and it's going to be right after
the spring releases it. So like, right, basically at the bottom, but like right after the spring is done. So you could set the spring energy equal to
kinetic energy because it's only going to have kinetic energy at that point. It won't have its H won't have changed yet, so it won't have lost any gravitational potential energy. So you could just say spring is equal to U or not kinetic energy, or you could say U gravitational up here is equal to kinetic energy, because you know that these are also equal from this. So you can solve part B multiple ways. Any other specific problems you want to go over? Do you want to copy any of this down, or can I just say this?
Yeah, I would.
Very complicated.
So is that use them like with the physics problems?
It's just like reading.
So some of them are with the physics problems, but they're usually the easier ones.
To some extent, you're not going to get the one where the ones that nobody solves.
Yeah,
Any of those.
like gravitational or the
Yeah. There'll be something to cover that topic probably, but it won't be something that nobody was able to solve that question. All of the topics that you can on the exam. If you want to review any of those.
friction. That's always hard.
Friction's always hard. What do you want to go over about friction or just anything? Oh, it's the boxes. Yeah. So we have and 2 and 1. They're going that direction. And 1 is 15 kilograms. And M2 is 88 kilograms. This one horizontally. Okay. So if locus holds with tension and 2 out of 30 newtons, what is the acceleration of the smallest rate? How would you balance?
Free diagram.
Of what?
Bottom.
I would say of the whole thing.
Oh,
Because it's small enough that the top crate will not slide. So the acceleration of the bottom crate and the acceleration of the top crate are going to be the same because they're going to move like they're one mass. So we can take the whole thing, make it into a point, and say that the only force acting in it is tension. So the sum of the forces A. The sum of the forces is going to be MA, is going to be tension. So acceleration, tension, is M total. Because it's both masses divided by M1 plus M2. For part A. And then just going to copy this. What about the verbiage?
What about gravity acting on the boxes?
That's down. So there is gravity. But this is in the y direction. Right? So it's accelerating in the y direction. It's not, there's also going to be a normal force. They're going to cancel each other out. So they don't really matter. Because the bottom surface is frictionless. If the bottom surface had a coefficient of friction, they would matter. It's just in this case that they don't. Copy. Okay. So the second part was,
What is the frictional force the lower crate exerted on the upper?
okay, so we're going to say that A1 gave us acceleration of both. And then it asks for the friction between the two crates. Yeah, so the frictional force that the lower crate exerts on the upper crate. So then we draw the free body diagram of just the top crate. Yeah. So what forces are acting on the top crate? Normal force. Up. Friction. Which direction is friction? This way?
Tension is
This way. Why? Do you want to explain why?
because when it's pulling on the right and the box wants to slide.
Yeah. The direction that the box would slide, if it could, is opposite direction. So of course friction can't move that. That's why the box moves with the lower box, because friction is what's making it forward. There's one more force.
Wait, if you pull the box in the right way, the box what's left? Yeah, this way.
Yes.
So then its friction is
Wait. If you pull the box which way?
this way.
So you're pulling the box this way. Which way will the box slide?
This way.
No. If the box was, okay, relative to this box, you're pulling the bottom box, so okay. See if I think that looks like this. I'm not sure if this kind of slippery enough. But if I hold this paper really quickly my pen would move that way, right? It wouldn't come with it. But if I accelerated the paper slowly, it would stay on, right? So tension is this direction, velocity would be that direction. So friction between the pen and the paper is what's holding the pen in this direction. The tension's that way, the pen moves that way. Of course, there's friction here, more friction here than there is here.
But opposite directions.
Yeah, but it's the same direction as tension.
Always.
Not always. In this case, it's always the opposite direction of where that object would have moved.
Mm-hmm.
So, yeah. So here there's also gravity. And one G. So, because this is static frictional force, it's not moving relative to M2. Let's say this is less than or equal to U at time 0. But because it's not moving, we could probably say it's probably going to be less. So this equation is not going to help us, right? Because it's going to be less than this number. But we found in part 1 that the acceleration is A. We didn't actually solve for it, so we have a letter for it. So the sum of the forces equal to MA equals the force of friction. So you can solve for the force of friction is equal to M1 times the value of A from part 1. Just that simple for part 2. So
we don't need to worry about tension.
in this case, no, because tension is acting on this box, not on this box. We did have to, you couldn't just solve part 2 without solving part 1, because you would, if you did solve part 1, you wouldn't know the acceleration. So you use tension to solve for the acceleration of the entire system, and then use that acceleration to apply to just the one box. Then what was the third one?
That's the maximum tension that a lower grade can be put at before the upper grade begins to slide.
Okay. So for part 1, when we solve for acceleration, we got acceleration is equal to T over M1 plus M2. So we know and in part 2, we solved that the force of friction is going to be equal to, between the two crates, M1 times A. And we also know that the force of friction is equal to US times normal force, which, if we look at this diagram, is equal to M1G. So we have and then if we substitute that, we get M1 tension divided by M1 plus M2. So you can use this to solve for maximum tension, because this is the maximum frictional force. Tension equals M1 G M1 plus M2 divided by M1. What's the next part of the problem? Or do you want to keep going on this problem? Tension is increased, causing the box to accelerate faster, and the top box begins sliding. What is the acceleration of the upper crate? So in this case, we have this acceleration for that box, but this box, the acceleration is going to be less. Right? So we can't solve for the whole thing, find acceleration 2, and then use that to find acceleration 1. That's not going to work. Instead, we're going to need to use free body diagram of this of M1. What forces are acting on M1 in this case? Friction. What direction is it in? The box, relative to this box, is sliding. So its velocity is in that direction. Yeah, so friction is still this way. That's kinetic friction is now time. We still have N. We still have mg. We still can get N is equal to mg from the fact that it's not going up and down. But then, for the x direction, if you use some of the forces x, all you get there is force kinetic friction. You solve for A is going to equal force of kinetic friction divided by mass. Go back over here. So then you get kinetic friction is just like static friction. Formula is mu k times normal force, which is mg, divided by mass. It's going to equal mu k times gravity. We see where that comes from.
In the last part, as the upper crate slides, what is the acceleration of the lower crate?
After the crate slides, what's the acceleration of the lower crate? Okay. We have the lower crate. What forces are acting on the lower crate? Tension. Yeah. Friction. Yeah. This surface is frictionless, but there is friction acting on this box because the box on top of it is sliding across it, right? So we have that force of friction. Yeah. And then normal force from that box, as well as a normal force from the ground, as well as its weight. And friction force we got to be equal to mu k times gravity. Which actually, now that I think of it, doesn't make a lot of sense. Let me look at this again.
Is
A.
Oh, acceleration, right, times
Times M. M1.
because it's the same as the original force acting. So, if we did some of the forces in the y direction, what do we have? I meant the x direction.
We have tension. And we have friction minus. And then we have that is going to equal to MA.
Right.
M2A.
So we're solving for acceleration.
Acceleration of box 2 is going to equal tension minus, we have FK is mu K G M1 all divided by M2.
Why don't we use the mass of M1 plus M2?
In this case, we're only asking for the acceleration of M2. And they have different accelerations in this case, so they're not accelerating together. M2 is technically taken into by all of these. That moving force is acting on the objects, but they're not moving as one object anymore. When they're moving together, then they can be one.
At the first problem,
Yeah. They're moving together, so they're moving like they're one object. So you can consider them as one. Oh, I have one more.
Okay.
The new blocks attached to the string above the first block. This part of this one or the whole thing? Because you only have 2 minutes. So okay, just this part, yes. Okay. So we have an incline. Oh, okay. Incline. Assuming we're given this angle, we have M1, M2. String. The new block is made of different material, so has a coefficient instead of friction of mu. So you have mu2. Okay. And then M1. Does M1 have a coefficient of friction? Did you?
Oh, at 21 first, what is the coefficient of kinetic friction between it and
Okay, so there is some coefficient of friction U2 is equal to some number. So, and we know the angle. So, what's the minimum mass? Mass 2. I would first look here to figure out what that tension needs to be to keep M1 from moving. So I would take M1. So there's tension, this direction, triangle force in this direction, energy in this direction, and also static friction in this direction. You can do forces in the x direction if you make this the x direction. It's going to be 2 plus fs minus mg sine of that angle. This is going to be normal force times mu s. So it's going to be mu 1 times mg cosine angle of that angle. So, and this is equal to 0 if it's static. So the minimum tension is going to be mu1 mg cosine of that minus g sine angle, oops, of that angle. And this is M1. So that would be the first box. You'd use that to find tension is going to equal that number, right? And for box 2, M2. And then there's tension this way, which we just solved for, so we can now ignore the first box. You have friction this way. And they're equal. Yeah. So you have mg. So when you do some of the forces in the x this direction, you get us of force minus tension, also minus the x component of the gravitational force. Oh wait, this is the tension. Minus mg sine angle. So you substitute in, this is going to equal 0. Mu s, the normal force is going to equal to the y component of the gravity, so you can say mu s mg cosine of that angle minus tension minus mg sine of that angle. You should be able to use this to solve for M2. But we are out of time for today. So, thank you.
You're welcome.
Good luck on your test.
I hope you guys do great.